NASA just spotted something today with 3 ILS. Nothing flashy, nothing that's going to make the evening news. But the people who've been tracking this interstellar comet for weeks, the ones who know exactly what they're looking for, saw enough to quietly return and update their models. No massive outburst. No spectacular new tail streaming across the sky, just a change. The kind of change that might tell you whether this thing is finally settling down or whether it's just catching its breath before doing something completely unexpected. If you've been following this comet, you know how strange its behavior has been, how unpredictable, how it keeps refusing to fit into the neat boxes we've built from studying comets that were born in our own solar system. Today's update doesn't answer all those questions, but it adds another missing piece in a puzzle that astronomers find both fascinating and frustrating in equal measure. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. So, here's what actually happened. The update started like every other day. Teams pulled in new images, brightness measurements, and position data from telescopes and spacecraft scattered across the solar system. They stacked everything against yesterday's best guess at what this comet should be doing. Most days, you expect small adjustments. The comet gets a bit dimmer as it moves away from the sun. The cloud of gas and dust around it quiets down a little. The orbit calculation might need a tiny tweak, but nothing major. That's the routine. That's what it happens with normal comets that follow the rules. That's not what the data showed today. The first thing they noticed was the brightness. When they plotted today's measurements against the typical model of how a comet should behave as it fades, I was still running brighter than expected. Not wildly off like it was a few days ago, but definitely not following that nice smooth decline the old prediction stated that it should. It's like the comet will not dim at the current rate. It's supposed to, holding on to its glow a little bit longer than the books say it should. This has been happening for a while now. This obstinate brightness, but what matters isn't just that it's brighter, it's how that brightness changes over time that tells the real story. So they did what they always do when there's inconsistency. They folded the brightness data over the rotation period, basically watching how the light changes as the comet tumbles through space. Every comet spins, and as it spins, different parts of its surface face the sun and face Earth. If you have active regions, jets of gas, and dust shooting out from specific spots on the nucleus, those will brighten and dim as the comet rotates, and those spots turn toward you or away from you. A few days ago, that light curve looked messy. Multiple peaks at different heights, timing all over the place like a heartbeat that couldn't find its rhythm. Too many things happening at once. Jets firing from different spots on the surface with no pattern anyone could pin down. It was chaos. Beautiful, fascinating chaos. But chaos nonetheless. Trying to model that kind of activity is like trying to predict which way a leaf will tumble in a windstorm. You can describe what occurred after the fact, but predicting the next rotation becomes nearly impossible due to the excessive number of processes fighting for control. Today's curve looks different. The main peak is still there, still the dominant feature. That's the big active region, the one that's been pumping out gas and dust consistently since we started watching. But those smaller bumps that used to spike and drop randomly between each spin, they've smoothed out. Instead of 3 or 4 ragged little humps scattered across the rotation, there are now 2 consistent secondary regions, smaller than the main peak, sure, but showing up at the same point in every single rotation cycle. It's like the comet went from chaotic noise to something complicated, but rhythmic. Still not simple, but no longer random. The difference between static on a radio and a song you don't quite recognize yet, but can tell has structure. That's the first subtle change. Activity hasn't stopped. The jets are still firing, still pumping material into space. But the way that activity shows up as the nucleus spins has become more organized. Those vents that used to flicker on and off whenever they felt like it now seem to have settled into a pattern. Maybe they've stabilized. Maybe the surface has reorganized itself somehow. Maybe we're just seeing the result of certain regions winning out over others in the competition for which cracks get to scream. Whatever the cause, the effect is clear in the data. The heartbeat has developed a rhythm. Then they looked at the comet cloud of gas and dust encircling the nucleus. The comet is where a lot of the comet's personality shows up. It's the visible consequence of everything happening on and just below the surface. Jets fire. Material streams out. Sunlight pushes on the dust grains. The solar wind interacts with the gas. And you get this glowing, flowing structure that can tell you volumes about what's happening at the center. You know how to read it. When the team stacked today's deep exposures and compared them to images from last week, you wouldn't immediately call it dramatic. The inner glow is still there. The tail still points away from the sun like it ought to. Nothing looks broken at first impression. If you were just scrolling through images casually, you might not even notice the difference. But zoom into the inner region, those first tens of thousands of kilometers around the nucleus, and things get interesting. In the earlier stacks, the inner coma had a bright, stretched, lopsided shape, thicker on one side, thinner on the other. Like something had been pulled too hard in one direction. It looked unbalanced, asymmetric-like. The nucleus was firing its jets unevenly and couldn't compensate. One hemisphere was doing most of the work, while the other stayed relatively quiet, creating this tilted, distorted glow that didn't match the neat, symmetrical halos seen around comets that behave well. That asymmetry has been one of the most enduring characteristics of 3I Atlas. Week after week, update after update, that lopsided glow kept showing up. It became the signature of this object, a thing that made it look stressed and unstable compared to the more balanced comets we're used to seeing. In today's data, the stretched bar remains there. This isn't a complete transformation, but it's rounder now. The brightest region around the nucleus isn't hugging one side as hard as it used to. The light has redistributed itself slightly, making the inner coma more symmetric than it's been in days. That sharp asymmetry that was screaming something's off balance has softened. Noggin, but definitely less pronounced. It's like watching a lopsided wheel gradually wobble less as it spins. Still not perfectly balanced, but closer than it was. Even the tail spine with its shining central line down the middle of the tail looks cleaner, less kinked near the base where it connects to the nucleus. The material appears to flow more smoothly and less turbulently. Again, these are subtle differences. You couldn't see them unless you were specifically looking for them, comparing images side by side with careful attention to detail, but they're real, and they're consistent across multiple observations from different telescopes. Subtle, not a transformation, but real. Sufficient for the modeling teams to take notice and start asking what could cause a change like this. And then there's the part that matters most to the experts in trajectory calculations. The orbit. This is where things get really technical, but it's worth understanding because it reveals something fundamental about how this comet moves through space. Every comet experiences gravitational forces. The sun pulls on it. The planets give it tiny tugs as it passes by. All of that can be calculated with exquisite precision. For active comets also experience non-gravitational forces. When jets fire, they act like tiny rocket engines. They push the nucleus in whatever direction the jets are pointing. If you have a jet firing from the sunward side, it pushes the comet away from the sun. If you have jets firing asymmetrically, they can speed up or slow down the rotation. They can nudge the orbit in ways pure gravity can't explain. Tracking these non-gravitational forces is crucial for predicting where the comet will be in the future. If you ignore them, your predictions drift further and further from reality as the comet continues to vent. Each update, they toss the most recent position measurements into their solver and ask a simple question. If we use yesterday's estimate for the forces other than gravity, the little push the comet gets from its own gas jets, does the model still match reality? Can we predict today's position based on yesterday's understanding of how the jets are firing? For the last several updates, the answer has been no. They've had to make big adjustments, rotate the thrust vector, point it in a new direction, change its strength, make it bigger, or chase whatever crazy combination of jets 3I Atlas was using that particular day. It's been frustrating, like trying to predict the path of a balloon that's leaking air from multiple holes that keep opening and closing randomly. Today, for the first time in a while, they didn't have to move it much. The extra acceleration from outgassing is still there. This isn't a dead rock drifting through space on a purely gravitational trajectory, but the direction of that push didn't wander away from yesterday's solution. The magnitude didn't jump around. When they let the software refit everything, it nudged the vector by a tiny amount and actually preferred a slightly smoother, more stable trend over the recent few days. That's huge. That's the kind of result that makes orbit analysts sit up and take notice, because it suggests the underlying activity driving those forces has become more predictable. The third subtlety is change. The comet is still pushing itself round with its own jets, but it's doing it in a more consistent way. The chaos is organizing. So line it all up. The light curve has smoothed out. Same main peak, but less chaotic noise between rotations. The inner coma has rounded out a bit, still active, but less sharply lopsided. The non-gravitational push hasn't disappeared, but it's settled into a more coherent direction that doesn't necessitate regular recalculation. That's what NASA means by a subtle change worth updating the model for. These aren't the kinds of numbers that get a lot of attention. You won't see this on the front page of news sites, but they're exactly the kinds of numbers that tell you something fundamental might be shifting inside this object. The kind of numbers that make scientists lean forward in their chairs and start asking deeper questions about what's actually happening beneath that icy surface. So what could have caused this? One possibility is that we're watching the comet finally begin to slide out of its most chaotic phase. Immediately following perihelion, when 3IATLAS made its closest approach to the Sun, it behaved like a nucleus with too many problems happening at once: shallow layers of ice blowing off from the heat, deep pockets of volatile material finally warming up and venting late, fractures opening in different directions as the surface cracked under heat stress, jets firing in ways that kept rearranging the spin of the nucleus, creating feedback loops where new cracks would open, change the spin, which would then change which parts of the surface got heated, opening more cracks. It's the kind of cascading complexity that makes prediction nearly impossible. In that regime, everything looks wild. The light curve is jagged because different regions turn on and off unpredictably. The coma is twisted because jets fire from all over the surface without coordination. The thrust direction wanders from one calculation to the next because the dominant gas source keeps changing as vents activate and deactivate. In today's data, you can see the first signs that some of those competing processes might be starting to align. The vents that are still active are becoming more regular in how they fire, instead of showing random on-off behavior scattered across the surface. A few dominant regions seem to be taking over and remaining active on a regular basis. That would naturally smooth the light curve. As the nucleus rotates, those regions would contribute light in a predictable pattern instead of flickering randomly. You'd see the same peaks at the same times in each rotation, precisely what the current data shows. It would also explain the inner coma rounding out. If activity is fed more consistently from a stable set of sources, the glow won't lurch from one side to another as violently. You'd get a more balanced distribution of gas and dust. The jets might still be asymmetric, but if they're consistent in their asymmetry, the time average structure begins to look more balanced. And a steadier pattern of outgassing means the net force on the nucleus, that tiny rocket engine we see in the orbit, calculations would start pointing in a more fixed direction. Instead of jerking around as different vents take over, the push becomes predictable. That's the optimistic reading. 31A TLAS is still active, still strange, but beginning to find a new equilibrium. The chaos is organizing itself into something more stable. The comet is adapting to its environment, settling into a configuration that works for its current distance from the Sun and its current rate of heating. There's a more cautious interpretation, though, and it's worth considering. We've seen comets do unexpected things before. Sometimes, before a stressed object fails completely, there's a period where the external signals briefly look calmer, not because the stress is gone, but because the system has locked into one dominant mode of response. If most of the remaining activity is now focused through a smaller set of fractures instead of being distributed across the whole surface, that could also make the coma look cleaner and the thrust look smoother. The light curve would organize because you're seeing fewer sources instead of many competing ones, but it could quietly be increasing the load on those particular regions. Think of it like pressure in a cracked dam, finding one major leak. From the outside, the water flows in a tidy, steady stream, organized, predictable, easy to model. Inside, that's not always a good sign. That one crack is taking all the stress that used to be spread across many weak points. Focused flow can erode the structure, accelerate the crack, and potentially lead to sudden failure if the material can't support the concentrated load. We've seen comets fracture before. We've seen them split into multiple pieces when internal stresses became too much. We've seen outbursts where trapped gas suddenly blows away chunks of the surface. The warning signs aren't always dramatic. Sometimes things look like they're settling down right before they come apart. We don't yet know which story 31ATLAS is telling. The data supports both interpretations. That's the frustrating and fascinating part of studying objects we can't visit, touch, or sample directly. We're reading tea leaves from millions of kilometers away, trying to infer the internal state of something we can only observe from the outside. What we do know is that today's data doesn't fit either extreme. People were hoping for or fearing. It hasn't stabilized into a quiet, fading rock drifting back into interstellar space. It hasn't exploded into obvious fragments scattered across its orbit. Telescope images would show multiple bright spots if it had broken up. The light curve would look completely different if the nucleus had shattered. Instead, the update says something more nuanced. It's still active. It's still being pushed around by its own jets. But the way that activity shows up, in the light, in the structure of the coma, in the orbit calculations, has become more organized. The chaos has structure now. The noise has pattern. That's the subtle change NASA spotted today. Not dramatic, not But significant if you know what you're looking at, significant if you understand how rare it is to watch an interstellar comet evolve in real time, responding to our sun's influence, revealing how an object from another star system behaves when it enters ours. If these trends continue over the next few days, a smoother light curve, rounder coma, stable thrust direction, we may be watching 3I Atlas ease into its outbound configuration, a new normal for an interstellar comet heading back into the dark, still active enough to be interesting, but predictable enough to model and track for months or even years as it fades. If instead, this calm is just a pause between larger shifts and the next update brings back jagged peaks, twisted coma structure, and wandering thrust vectors, then this moment is merely a breath between Saprizia's false dawn before another chaotic phase. Regardless, these minuscule updates matter more than you might think. With interstellar comets, we learn not just from dramatic events, but from subtle changes, the ones that tell us how an alien visitor tries to hold itself together under stress, how it responds when heated in ways it hasn't experienced for millions or billions of years, and whether its structure adapts or fails. Every small update adds another data point to a story we've never been able to tell before. We've only observed a few interstellar objects. Oumuamua was the first, and it raised more questions than it answered. Borisov was the second and looked more like a traditional comet, but still behaved differently in subtle ways. Now 3I Atlas is the third, reminding us again that we can't assume these visitors will behave like the comets we grew up with. Each one teaches us something new about what exists between the stars, how these objects form in other solar systems, how they're ejected into interstellar space, how they survive millions of years traveling through the cold void, and what happens when they fall into someone else's solar system and get cooked by a star that isn't their own. 3I Atlas isn't done teaching us yet. Today's update is just another subtitle, perhaps, but chapters like this determine whether the ending will be calm or chaotic, whether the comet holds together or comes apart, whether it fades quietly or goes out with a bang. So if you want to know whether this smoother heartbeat and more rounded coma mark the version that finally carries it out of our solar system intact, or whether this is just a setup for another surprise, want to keep watching. This story isn't over, not by a long shot. Every day brings new data, new measurements, and new chances to learn something we've never known before. Stay curious,